Hello, dear friends and colleagues. Welcome back. Today we're going to talk about capacitance and Tan Delta testing. This is just the first video, and this video will answer the question, why are we doing this test? What are the reasons for Tan Delta testing? So let's start answering these questions. First, let's say, what is a Tan Delta test? So CNTD, or Tan Delta, or DF, or PF, which is a little bit different, but we'll explain the differences later, is a test, most common technique used to assess the insulation of electrical assets, whether they are transformer, motor, circuit breaker, generator, current transformer, voltage transformer, surge arrestor, or some other asset. It's important to emphasize that this is an AC test. So in the past, there were a lot of tests which used DC voltage. One of them is very common on a transformer. It's 5 kV test, polarization index test, and those tests are good, but AC test is even better for a few reasons. First of all, the results are more repeatable, while with the DC they're less repeatable. And the other reason is that DC testing tends to be more destructive than AC testing, since it leaves some free electrons inside the insulation, and in case that insulation had some voids, imperfections inside, you're increasing the probability of partial discharge inside that particular insulation. So we use this test to see if our asset has had some mechanical deformation, and to see what is the state of our insulation, how old is our insulation, and how much more time do we have until it fails. So this test will help us, for example, to do some predictive maintenance. So it's also important to emphasize that test is performed always between two different potentials, and here we are starting to introduce the concept of capacitor. Why are we mentioning here capacitor? Well, before we answer that, let's just define the insulation. Insulation is, as IEEE defines it, material or a combination of suitable non-conducting materials that provide electrical insulation of two parts at different voltages. So in short, insulation is something we put between two conductors if we don't want any electricity running between these two conductors. So let's say now we say here at different voltages. So if we have two different voltages, each on one side, and we have a dielectric in between, dielectric or an insulator, does this sound familiar? Well, actually, it sounds quite familiar because this is more or less the definition of a capacitor. Capacitor has two conductive plates and a dielectric in between. So this can be high voltage side of your transformer, and this can be a low voltage side. This can be high voltage side of a transformer, and this can be maybe the ground. Or this can be a low voltage side of the transformer, and this can be the ground. Or this can be maybe the stator of your rotating machine, and this can be the ground, or this can be rotor, and this can be stator. So as you can see, the reason why we model the insulation with a capacitance is that if you put two different potentials close to each other and a dielectric, an insulator in between, you cannot avoid to get a capacitor, and the capacitor has a certain capacitance. So you can call it a parasitic capacitance. You might not want to have it there, but it is there. It's a physical reality. So if it's a physical reality, let's use it. Let's use it and see how it helps us to determine the state of our insulation. So in order to see how it can help us, let's remember what is the formula for the capacitance of the most simple capacitor, which is this capacitor here, so two-plate capacitor. And the formula is epsilon A divided with D, where C is capacitance in farads, epsilon is permittivity of dielectric, A is area of plate overlap in square meters, and D is distance between plates in meters. So here we can see that if after having measured a certain capacitance for the first time, and thus having obtained our reference value, if we measure capacitance after a while and there is difference between the first measurement and the second measurement, we can say that some of these parameters have changed. Maybe only one has changed, maybe two have changed, maybe all three have changed, but in general we're going to say if epsilon has changed, then the characteristic of my insulator has changed, and if A and D have changed, then the geometrical movement happened inside, and this capacitor, this asset, now has issue with certain physical geometrical movement inside. Just to remind ourselves, epsilon is, as we said, permeativity of dielectric. It's actually epsilon is you get epsilon when you multiply epsilon 0 and epsilon r, so relative permeativity and absolute permeativity. And absolute permeativity is a constant, while relative permeativity is relative, as the word says, and each material has a different number. So vacuum has 1, porcelain has 2.2, let's say, paper, oil has 2.2, porcelain has 7, which would effectively mean that you can put 7 times more electrical charge in a capacitor which has porcelain as dielectric in comparison to a capacitor which has vacuum as dielectric. So this is epsilon, and let's see how we can now use this. So let's talk for a second about an ideal capacitor. In a capacitor, we know that the current and voltage are shifted in phase 90 degrees, which is the definition of ideal transformer. Current is leading, voltage is lagging. And we can see that system here, AC source and the symbol for ideal capacitor. Now, there is also something we call real capacitor, and that fellow does not have phase shift of 90 degrees, but it has a smaller phase shift. That is because in an ideal transformer, there is no in-phase current, resistive current running through the insulation, and there is no resistive current because that transformer is ideal. But moving on, we will find out in life that the same way that there is no ideal man or a woman or a boss or an employee, there is no ideal capacitor. So how can we make this ideal capacitor realistic? Well, we can make it realistic by adding a resistor in parallel with our previous ideal capacitor, and we are doing this simply because as much as the insulation tries, there will always be at least some small, finite, resistive current running from one plate of the capacitor to another. So in order to describe that resistive current, we are adding a resistive element. The angle between these two currents is also 90 degrees, which would actually, with which we come to the point that we will have now voltage coming from here, current leading 90 degrees, and then we will have here another current which will be in phase with this voltage. And this is actually the reason why we measure tan delta, because we have some current in phase with voltage, and when we have current in phase with voltage, we have power dissipation. So since there is no angle, we can just multiply these two numbers. So let's say that we have 10 kilovolts voltage and that we have a huge resistor which allows only 1 milliamp to pass through it, which would mean that we are actually dissipating 10 watts on this insulator. Now 10 watts is not much, but 10 watts is power. If we multiply power with time, we get energy. So in 1 hour, we are going to lose 3,600 joules or 10 watt hours in this insulator which has only 1 milliamp running through it. So this is now important because what happens here is that we have a heat on our insulator, because all this energy which we see here turns into heat, and heat degrades the insulating properties of our dielectric. So heat hurts our insulator, and heat is not something we want to have. That's one of the reasons why transformers have fans, why they have a cooling system, and not only transformers, many other electrical assets, including, let's say, your computers, etc., etc. So, as we were saying, this heat is a problem because it damages our insulation. And with the heat being constantly applied on the insulator, the insulation starts to degrade, which as a consequence has increase of resistive current. Lower insulating properties, higher resistive current. But as the resistive current increases, more heat is dissipated. More heat in return additionally degrades the insulation, which now allows more current to flow, and as you can see, it's a chain reaction which will keep going until the insulation totally and completely fails. So in order to stop this type of breakdown, in order to predict this type of breakdown, we are going to measure tan delta. So hopefully we have answered the question, why are we measuring? We are measuring it because we want to know the state of our insulation, and the insulation has a very non-linear characteristic. It has a very non-linear characteristic, and you could, for example, maybe compare the insulation to, let's say, a dike. In Netherlands, you have a lot of dikes dividing sea from the land. Dikes are huge. It's just a huge mass of sand, probably with some steel, maybe concrete inside, which keep the water outside. Now, there is this thing, it is known fact that if you see a dike with a small hole, you need to alert, and everybody knows that in Netherlands, for example, you need to alert everybody as soon as possible, because a small hole will very soon grow to be a slightly bigger hole, and a slightly bigger hole will very soon destroy the whole dike, because the processes inside. We cannot see what the water does to the dike inside, but I assure you that the dike, which has a small leak, even the smallest leak, is compromised and needs to be fixed. The same is applicable to our insulation, and that's why we always want to see at which point is our insulation, so that we can predictively assess our maintenance, and so that we don't have any kind of faults on our assets. So this was it for the first part of our Tan Delta series. Thank you for your attention, and see you in the next video. Bye.